In this video, we'll talk about analysis of signals and LTI systems, and we see what is the difference between deterministic stochastic processes, deterministic signals versus stochastic random processes. There is a challenge, of course, when you deal with the stochastic processes. So when we have a linear time invariant system, an LTI system, if your input is x of t and then your output is y of t, we know that for any LTI system there exists h of t, and h of t is basically the response. If you give delta t, unit impulse response, then you get h of t. Then for any other output, y of t is equal to x of t, a convolution integral with h of t, which is equal to integral of, let's say, h of t minus alpha times x of alpha t alpha, and then alpha is a dummy variable from minus infinity to plus infinity. So this is for deterministic signals. Of course, if you take Fourier transform of both sides of this equation, this convolution integral becomes a multiplication of Fourier transforms of input and Fourier transform of unit impulse response. That means that the convolution integral, which is a fairly complex integration, becomes a very simplified amplification. That means that in each frequency, the corresponding component of the input is either amplified or attenuated or remains constant. So when we deal with deterministic signals and LTI systems, everything becomes easy and simple. In frequency domain, they become complex. So in that case, we can have convolution, and then these convolution can be analyzed in frequency domain. In frequency domain, y of f becomes simply equal to x of f, which is Fourier transform of the input times h of f, and the Fourier transforms are complex signals. Now, if we consider a Fourier transform of a random process for stochastic signals and deterministic input, the question is that can we do that? So it's kind of like this big question. So, of course, in this case, if my input is x of t random process and I give it to an LTI system with impulse response of h of t, somehow I have to define y of t, and y of t becomes the same convolution integral, x of t and then convolution with h of t, which is equal to integral of the same dummy variable alpha from minus infinity to plus infinity, h of t minus alpha, and then x of alpha t alpha. Of course, subject that this integral converges. Now, the question is that can we use Fourier transform? And the answer is no, because I cannot define Fourier transform, because Fourier transform of x of t for a signal, here for a stochastic process, is equal to integral from, let's say, t from minus infinity to plus infinity, x of t, and then e to the power of j omega t dt. The trouble is that these integral, in most cases, do not converge. Because, for instance, consider omega to be equal to 0. That is the DC component. So this will become, this integral is the sum of all the components of your signal. If it would have been a discrete time signal, this would be a sum of infinite number of random variables. And obviously, this does not necessarily converge. So we have a convergence problem. So this might become often infinity, not having finite variance, and so on. So the same applies to y of t. The Fourier transform of these does not exist. So in that case, the convolution is valid, we can use it, but the Fourier transformation of x of t does not exist. Fourier transform of y of t does not exist. In this case, what we can do? And the answer is that this chapter tries to find an alternative solution for that, which we call power spectral density. So instead of using Fourier transform of x of t or y of t, which don't exist, we will talk about something else. We will find another alternative solution. So we cannot do that, and the Fourier integral, they don't exist. They are meaningless. And we are lucky that Fourier transform could be applied on statistics of these functions. For instance, if you take mean of x of t, then we may apply Fourier transform on that. Or if you take r x of t1 and t2, under certain circumstances, Fourier transform of these could be used. And then we have to establish relationships about that.